Welcome to lesson 65. Remember when we solved for radicals within an equation, we would have something say like this. Let's say x minus 3 minus 2 is equal to 0. Well, we would isolate the radical by eliminating anything on the side of the same side as the radical, and then that would allow us to solve to get the radical on its own. Then all we would do is square the radical, and because we did it to one side, we would do it to both sides to keep it balanced, and we would end up eliminating the radical and bringing it back up to numbers that we could actually solve for. So x minus 3, we would add the 3 to both sides, and x would be equal to 7. So we were able to solve for that. And then what we would do is we take that x and we put it back into our radical and check it and make sure it works. So 7 minus 3 minus 2 equals 0. 7 minus 3 is 4. Square root of 4 is 2 minus 2. And that does check out. It is 2 minus 2 is 0. So we're going to do this exact same thing with trigonometric functions. So here we have 65.1. We're going to solve the sine of theta minus the square root of 1 minus sine squared of theta equals 0. And that given is that we are in one rotation of the coordinate system. So first of all, let's isolate our radical. And whenever that radical is negative, we don't want to move sine, we want to move the negative so that we have two positive values that we're working with. So I'm just going to add this to both sides. So then this becomes the sine of theta is equal to the square root of 1 minus the sine squared of theta. So now I square both sides, and I get the sine squared of theta is equal to 1 minus the sine squared of theta. And now I can reverse the process. Now that I have some whole numbers to work with, I can subtract this, subtract the 1 and add the sine number to both sides and bring it all back and set it equal to 0, which will allow me to then factor it. So I'm going to do that now. So as you can see, now I have 2 times the sine squared of theta minus 1 equals 0. We don't like to solve these with a coefficient. It makes it more difficult. It muddies the water. So we're going to get rid of that lead coefficient just like we would have in a polynomial, and we're going to divide everything by the lead coefficient. Now if we're very careful and we pay enough attention, we see that this could be treated like a perfect square, except for this 1/2. This fraction here. We have to think to ourselves, what times itself gives us 1/2? Well, if you think about 1/2 and you think about radicals, then you know that if we were to take this and turn it into a radical and multiply it times itself, 1 over the square root of 2 times 1 over the square root of 2 is going to equal 1/2, because square root of 2 times square root of 2 is 2. So we can factor this as a perfect square using the radical version. So I'm going to do that now. So now that it's factored, it's really easy to see what our possible solutions for the sine of theta would be. And that would be the sine of theta is equal to a positive 1 over the square root of 2 and a negative 1 over the square root of 2. Now we need our unit circle in order to solve and see what these degrees of measure actually are. So I am going to be looking at the answers for the sine of theta on our unit circle and see what I can find as far as what theta would be equal to. These are some possible roots for theta. So a positive 1 over the square root of 2, let's look and see what we can find. I'm looking at these, and I'm looking at 45. If you remember, these are all rationalized. So what that means is we took the square root of 2 over 2. We can unrationalize it, right? So we can take the square root of 2 over 2. We know that we multiplied this number by square root of 2 over 2, so we're going to divide by the same number, which means we're going to multiply by the flip. So that's going to be square root of 2 over square root of 2. And that is going to be equal to 2 over 2 times the square root of 2. This resolves into 1. So we're left behind 2 times 1. Those factor out. This is equal to 1 over square root of 2. So anything that has square root of 2 over 2 is going to be an angle that we are looking for. So 45, 135, here's a negative version, and another negative version. So our 4 possible answers are going to be 45 degrees, or 4 possible roots, I should say, 135 degrees, 225 degrees, and 315 degrees. So now we need to test and see if those roots actually work. So let me give us some room over here, and I'm going to run those numbers for us. So having done the numbers, what I did was I set them back equal to each other. I went back to our equation where they were equal to one another. Sine of theta is equal to square root of 1 minus the sine squared of theta. So that was the equation I used to solve, because that's the only way to set them to find out if they were equal. Now we could have done this and set it equal to 0. That would have worked as well. But this is an easier check because it sets them equal to one another, which then allows us to really determine if they are indeed equal. So you can see that the sine of 45 degrees and 135 had a positive result. Both of those are set equal to each other. But the sine of 225 and 315 degrees gave us a negative and its opposite. Same number, just opposite values. So they were not equal to one another. So therefore, 225 and 315 are not valid roots of theta. So our theta answer is 45 degrees and 135 degrees. All right, so when we check the possibilities, or we check these possible roots for each one of these, we find that we either have the tan of x is equal, or x is either equal to 60 degrees, 240 degrees, or 270 degrees. And we got there by, let's go back up here, we had to set each one of these equal to 0 because these are both already factored for us. So we said the tan of x minus square root of 3 is equal to 0, or the sine of x plus 1 is equal to 0. So then we added square root of 3 to both sides, so the tan of x is equal to the square root of 3. We turn that into a fraction by putting it over 1. So then we look around our unit circle and we find square root of 3 over 1. Remember, it's opposite over adjacent for tan. So that would be at the 60 degree mark, and then we went around the circle, we found the negative square root of 3 over the negative 1 would make it a positive, and that's at the 240 degree mark. So 60 and 240 degree for the tan of x equal to the square root of 3. So x is equal to 270 degrees because negative 1 over 1, which is what you would get if you subtracted 1 from both sides, we would look around for the opposite over the adjacent. That would just equal negative 1, right? So we would look for the sine of negative 1, which would be at 270 degrees. So what we did was we went in and we substituted all these values in for our possible x. So first we started with a 60, right? Now we know that one of these is going to be 0. Well, we know the sine of 60 degrees is not 0. So that can't be the 0 term. However, the tan of 60 degrees minus the square root of 3 equals 0 is a true statement because the tan of 60 degrees is the square root of 3 over 1. If you look here, square root of 3 over 1. So that works out. That is the square root of 3. So the tan of 60 is a possible solution. We look at 240 minus square root of 3 equal to 0. Then yes, because both of these match these already, we knew they would solve out. But we're just showing you negative square root of 3 over negative 1 is a positive square root of 3. So 240 is also a possible solution for x. However, x is equal to 270 degrees. Our sine, when we sub that in, we get tan of 270 is equal to square root of 3. But the tan of 270 is not the square root of 3. It is negative 1 over 0. It's negative 1. So we can't, it's undefined. We cannot solve it. It is not equal to the square root of 3. So therefore, it is not a solution set. So our solution set is 60 and 240 degrees. All right, let's move on to 65b. In the next video, got a few practice problems like this for you to solve. We're going to talk about graphs of logarithmic functions after you do a couple practice problems for 65a.